chapter 9 is where chemistry really starts to get interesting. It becomes the chemistry that we sort of think of as being chemistry. We are actually going to start dealing with chemical reactions. And the easiest way to think of a chemical reaction really is just rearranging atoms. That's all we're doing. We're rearranging atoms. If you remember the law of conservation of matter, you can't create new matter and you can't destroy matter in chemical reactions. So really, all we are doing is rearranging how it is. We're rearranging what it looks like. We have our textbook definition here. The process by which the atoms of one or more substances are rearranged to form different substances. But really, we're taking atoms and we're moving them around to make a different pattern, essentially. If you're familiar with Legos, okay, it's like you can take one thing that you've made out of Legos and pull it all apart, and you can make something else with those same pieces. That's pretty much what we have going on. Okay. How do you know when a chemical reaction is happening? Sometimes you don't. Sometimes you can't really tell. If we were to go into the lab, I could mix a couple of clear liquids and there would be a chemical reaction happening, but it would just be some clear liquid in container. You wouldn't be able to tell. Other times, it's very, very obvious that we have some sort of reaction coming. The book goes through several different things that might be an indication of, some sort of chemical reaction. One is a temperature change. If you mix two things together and they either get warm or they get cold, there's a good chance that we have some sort of chemical reaction going on. Another temperature change would be like combustion. If you're burning something, obviously there's a temperature change going on there. So basically, if you're mixing things and the temperature changes either direction, you might be dealing with a chemical reaction. It's not a guarantee. There are some other things that can happen that change temperatures that are not chemical reactions, but there's a good chance that it is. Some other things it gives pictures of, so color change. Sometimes when you mix two things, you're going to get a color change. It gives the example of that apple. Everyone knows that if you're eating an apple and leave it out on the counter, it turns brown. Okay? That's a chemical change. That is a chemical change. And a lot of times color changes can indicate something, some sort of chemical reaction is happening. It also gives the example of like bubbles. If we were to take two different things, mix them together, and we start to see bubbles forming, there's a good chance there's a chemical reaction going on, because what's happening typically is as you're rearranging these atoms, one of the things that you're forming is a gas rather than a liquid or solid like you may have started with. And so you've made something new, which is a gas, and so it bubbles out. The formation of a solid is also listed. So if you have something that is not solid at the start, and when it finishes, it is solid, could be a chemical reaction. Just like all of these things, they're not an absolute definite. It could be that you're seeing these things and there's no chemical reaction happening, but there's a good chance that if you're seeing these, they are happening. So now we need to know how to talk about chemical reactions, because that's what we're going to spend a lot of the rest of the year talking about, is chemical reactions, different types, and how different things behave in different circumstances. And we have seen, I've written chemical reactions on the board before, but now we really need to start being able to interpret them. Okay? And the book, you know, gives sort of this just really basic outline of how we do this on page 283, and it writes, reactant 1 plus reactant 2, and then we put an arrow. So that arrow tells us that we are no longer with our starting materials. Our starting materials are called reactants. And we separate the starting materials from the ending materials with this arrow. And we call the ending materials products. Okay. Just to keep the format, we'll say product 1 plus product. Now, it doesn't have to follow this exact pattern. It doesn't have to have two things making two things. We're going to see plenty of examples where we don't follow this exact pattern, but that is pretty much just the general idea. Okay. Now, I do want to mention there are some symbols. Okay, there's a table on page 283 of different symbols that we are going to be interested in when we are making these chemical reactions. Now, we have the plus symbol. Basically, that just means, well, as it says, it separates two or more reactants or products. So you put the plus in between either reactants or products. The arrow separates reactants from products. You can have a double arrow. You may see this a little bit. That indicates what's called a reversible reaction. And we'll talk more about reversible reactions in a little bit as we go through the class. But really what it's saying is you can take these reactants, react them together, and make these products, but these products can also react together to make the initial reactants. So the reaction can go both directions. That's what we mean by reversible. Like I said, we'll talk more about that, not today. But just in case you ever see that double arrow, that's what it means. And then we have these 4 symbols that indicate the states of matter. And we find them at the end, right behind these reactants, or the products. So, for example, so this is hydrogen. That G right there means that we're dealing with hydrogen gas. We put an L, liquid, okay? If we, let's dealing with magnesium metal, that S being solid. Then we have that AQ. Aqueous is what that stands for, aqueous. And what aqueous means, it's dissolved in water. That's all it is. So sodium chloride, that's just regular table salt. But if we put that AQ right there, that means we've taken some sodium chloride and dissolved it in water, and that is what's being put into it.
So AQ is meaning sodium, but even dissolved in the water.
So it means this whole thing has been dissolved in water.
Oh, okay.
So that's what the AQ means. It means you have something that is dissolved in water. Okay. So those are the symbols that we're going to use. I will admit, a lot of times, I'm guilty of forgetting to put the state of matter when I write equations. I should write them all the time, but sometimes I'm just too lazy to do it because in my mind, I can see what states they're going to be in without having to write them. But anyway. So let's look at some examples of actual chemical reactions, and we'll sort of give some real, this is how it's done, because obviously that is just sort of a general guideline of how to write it. Now, the first way that we can write chemical reactions, and this is not the way that we will do it most often, but we use what's called a word equation. And that's where we literally write out every single thing that we're dealing with. And there's an example on 284 at the top where it says word equations. And it's actually, you can see a picture of what's happening there. Kind of a weird looking brown gas, whatever you want to call it. But we have aluminum and we have bromine. Okay? And like I said, with word equations, we actually write everything out. So we write aluminum is a solid plus bromine, which can be a liquid. Okay. So those are the reactants, what we're starting with. We put our arrow, and what we end up with is solid aluminum bromide. Okay. So that's a word equation. You can write a word equation for every single chemical reaction ever. Pretty straightforward. You just have to write out what it is. Okay? But that takes too much time. Now, the easy ones are just the straight elements. Okay? So aluminum is Al. That's pretty straightforward. Now, bromine, we can look on the periodic table and we see it's Br. It does take a little bit of experience to know that it's going to be Br2. The halogens form these what are called diatomic molecules, where there's two of the same things and they bond together. So, I mean, I know that. That's just kind of it comes with experience. But yeah. And then aluminum bromide. Now, when we talked about ionic compounds, you should be able to figure out what the ratios for this will be. Aluminum forms +3, bromide -1. So we need 3 of the bromines. Okay. So this is our skeleton equation. So if you were asked to write a skeleton equation, that's all you need to do.
Oh, I hated those last two.
Yeah, we haven't even gotten to the real fun part yet. So these skeleton equations, see, I didn't even put the dates in there already. Skeleton equations tell us what is involved, okay? But it's a shorter way of writing out than the word equation. But it's not quite finished. Can anyone see why we need to change something here?
Oh, like the bromine.
What about the bromine?
Change it to IB.
Oh, no, because this, it only changes to "ide" when it's in the compound, but that's a good thought. Or something else?
Because the bromide has to hang on the reaction, and then actually
We have this magical extra bromine atom. And remember, we can't do that. We're not allowed to do that. All right? So to make it what's called a chemical equation, we need to account for that. And so now comes something that will never, ever go away as long as we are in chemistry. Balancing the equation. Balancing the equation. And it really is sort of like, balancing anything. Okay? Figure out where the midpoint is. Right there. Okay. So to balance something, you have to have the same amount of mass on both sides, right? Right now, this has too much. This is not balanced because there's the extra atom right there. So we need to figure out a way that we can fix that. Now, it would be super nice if we could just do this. That would make things super easy. But you can't do that. Because bromine does not form Br3, it forms Br2. Okay? So the only thing that we can change is how many of each one of these we have. You need to think of these as complete units. And you can only deal in complete units. Okay? You can only deal in complete units. So the way I like to do this, the way that I always want to balance my equations, I start out by just listing all of the elements that we have. So we have aluminum, we have bromine. So we make our little chart here, and this is the product side, and that's the reactant side, or we'll switch those because that goes left to right like the equation. So, reactants. How many atoms of aluminum do we see right here? 1. Okay. How many atoms of bromine do we see right here? 2. All right, now let's do our products. In this molecule, how many atoms of aluminum do we have? 1. Now that's nice because they're the same, but when we look, we have 3 atoms of bromine. Okay. So when we do this chart, we can see we have too much bromine. So we need more over here. Now, if you don't put anything there, it's implied that we have 1. Okay? We just assume that means 1. As you'll see, and as we've already kind of talked about today, in chemistry, if we can get away without writing something, we're going to. Okay. So if nothing's there, we assume it's 1. And if we need to add another one, now we put 2. So if we put a 2 right there, now how many atoms of bromine do we have total? What? 4, right? Because each molecule has 2, so we have 2 molecules. So we have 4 total atoms of bromine on this side now. Okay? Did that balance it? No, because we still don't have the same number here. But now we need more bromine on that side. So if we put another one there, change it from 1 to 2, now how many atoms of bromine do we have over there? 5. We have 6, because remember we have a total of 3 atoms in each molecule, but we have 2 molecules now. So whenever you're figuring out how many atoms you have, multiply that subscript, the little number below it, by the coefficient. That's what we call this, the coefficient. So 3 times 2 gives us 6. But what else has changed? We didn't just change bromine. We changed aluminum too. We changed everything in that molecule. So now we have 2 there. And it seems like we're just getting further and further away from being balanced, doesn't it? We're not. We are moving in the right direction. Okay. So now, honestly, we need more aluminum and we need more bromine. We need more of both. We can pick whichever one we want. Let's just pick aluminum. So we have 2 over there. We have 1 here. What do we need to do to this? We need to put a 2 in front of it, right? So that we can have the same number on both sides. We put a 2 right there. Well, our aluminum is now balanced again. If you write the right number, there it is. Okay. Now we just need to figure out bromine. We have 4 here. We need 6 to match that. What can we change with that bromine to get to 6? Oh, change the 2 into a 3. So if we put a 3 right there, now how many atoms of bromine are we going to have? We're balanced. Okay. Balancing equations, it's one of those things where a lot of people struggle with it right at first. But once it clicks, like once you figure out what we're doing, it actually just sort of becomes easy. Okay. And the only way, if you're struggling with balancing equations, the only way to get better at it is practice. Okay. And like I said, this is never going away. Equations always have to be balanced. From now until the end of chemistry, equations have to be balanced. So if it's something that you end up struggling with, we need to practice. Okay. There are actually a lot of good resources for practice. So if it's something you're struggling with, let me know, and I will get you some of those resources. Okay. We're going to do practice together in class. We're going to practice a few of them because I know there's a lot of moving parts. If I sit down to balance an equation, I've done it so many times that I can pick which ones need to be done first. See, we started by this bromine and put a 2 there. It ended up not being a 2. Okay. Once you do it enough, you're going to get to the point where you'll be able to see, oh, well, I've got a 3 right here. There's no way I can make 2 bromine equal 3. Like that, it just doesn't work like that. And so if I were doing it, I would immediately at least start with 2 here because I know I need to have an even number. Okay? Those are little things that as you go through and as you practice, these are just the little things you're going to pick up on. Now, did we eventually get to the right answer? Yes, but it was just an extra step. Okay? So that's what the practice is going to get you. It's going to get you where you're comfortable and where you are able to balance these a lot quicker. The other nice thing about balancing equations, you can always, 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 always check your answer to know if you're right. Because it's just a matter of counting. You can all count. All right? To check our answer, we have 2 aluminum. We have 2 aluminum. It's the same. We have 6 bromine. We have 6 bromine. It's the same. If you can count up all the different atoms and they're the same on both sides, you have balanced correctly. We just need to make sure we have the same number of things on both sides. That's really all it is. Okay? And like I said, as you practice, it becomes easier, which is why we're going to do some more practice. So let's pick another one. In fact, we'll go to the next page in the book. There's an example problem that we're going to work through together. Now this one is, it gives us, write the balanced chemical equation for the reaction in which aqueous sodium hydroxide. Now what does aqueous mean again? The AQ? It's dissolved in water. So we've taken solid sodium hydroxide and dissolved it in water. Okay. So aqueous sodium hydroxide and aqueous calcium bromide react to produce solid calcium hydroxide and aqueous sodium bromide. So there's a lot of things going on. Okay. We've got 4 different things that we need to get in the right spot first. So first, let's identify what are our reactants. What are we starting with? Can you see what are we starting with? So if you're looking for the problem, it's page 287. Our reactants are in the word before it says react. Okay? So we have aqueous sodium hydroxide, which is that. It's an ionic compound. This is why we took the time to learn how to name ionic compounds, so that when we get to this point, we can pick them out. Okay? And it's aqueous, so we have the AQ. And then we also have calcium bromide. Calcium bromide. Once again, if we go through our ionic charges, calcium is going to be +2, bromine is -1, so we need 2 bromines to balance the charge. Okay, so this is what we have. So those are the reactants. That's what we're starting with. Okay. And then it tells us we're going to produce solid calcium hydroxide. Once again, this is ionic compounds, balancing charges. Calcium with a 2+ charge. Hydroxide has a -1, so we need 2 of them. Okay. And aqueous, I'll put the solid there. And aqueous sodium bromide. Sodium bromide. These are, sodium is +1, bromine -1, so 1 and 1. All right. Honestly, that's probably the hardest part, getting those set up. So now, let's list our different elements that we have. So we have sodium, we have oxygen, hydrogen, calcium, and bromine. Okay. Now I know you may be thinking, we only had 2 elements in the last one and now we've jumped up to 5. Is this really something that we can do? It is, okay? Don't be afraid. Let me get it. So first, let's just count. On our reactant side, how many atoms of sodium do we have? 1. Okay, right there. How many atoms of oxygen do we have?
1.
We have 1. It's right here. What about hydrogen?
1.
1. Calcium?
1.
1. And bromine?
2.
This one we have 2 of. Okay, so we've gotten all of that for our reactants. Let's go over to the product side. Sodium. How many atoms of sodium do we have? 1. Look at that, it's balanced. Yay. Oxygen. We actually have 2 of those. Hydrogen. 2 of those. Calcium. 1. And bromine.
1.
1. All right. Where do we want to start?
Oxygen. We work our way down.
You want to start with oxygen? Okay, we can do that. Where do we need to add more oxygen? Which side? Okay, to our reactants. So what are we going to do? You want to put a 2 right here? All right. So that does change our oxygen. But what else does it change?
Sodium.
Changes our sodium and
Hydrogen.
our hydrogen. Okay. What do you want to do next?
Add the sodium back.
So we're unbalanced on sodium. You want to tackle that next?
Yeah.
So you want to put a 2 right here?
Yeah.
Yes? Yeah. Okay. So that does change our sodium to 2. What else does it change? is our bromine. Look at that. Changes it to 2. We are balanced. Okay. Now I will just mention, this is not something that you need to do. If we're dealing with hydroxide or really any other polyatomic ion, remember these polyatomic ions stay together in the reactions. Okay? So really, we could have treated this as one thing. We could have said, instead of having oxygen and hydrogen, we could have put OH. If that makes sense to you, it can be a shortcut. If it doesn't, don't worry. Just separate them out like we did. Okay? You don't need to be worrying about shortcuts until you truly understand this. Okay? All right. Let's do another practice just because, like I said, this skill is never, ever, ever going to go away. Yes?
Just real quick, that board down there,
Mm-hmm.
turns out it didn't come from, it was taken out of a college that
Oh, okay.
they were shutting down. And so they just went and got it. So there are some pieces that we don't have.
Okay.
But she is actually looking into it to make sure that we get it.
Awesome. Okay. Let's look at, so we're going to stay on 287. We're going to look at one of these practice problems. Let's just do number 4. So in water, iron chloride reacts with sodium hydroxide, producing solid iron hydroxide and sodium chloride. Once again, the hardest part is going to be going from that word equation to the skeleton equation. Okay, because this requires the, the naming skills and all of that we have talked about. So, now it does say in water, so we're going to be dealing with aqueous reactants. Iron, if you notice it says iron 3 chloride, that tells us that we're dealing with the +3 ion of iron. Okay? Because remember, with these transition metals, they can form, a lot of them can form different charges on the ions. When we put that 3, it says it's the iron +3. So that tells us we need that, okay? Because +3, all 3 of these are -1, it works out. And as we know, it's aqueous. All right. Reacts with sodium hydroxide. Ooh, that's nice. We already did this one. We know that. NaOH. Very good. Also aqueous. Okay. Producing solid iron hydroxide. Okay. And it's solid. And sodium chloride. Yeah, sodium chloride, NaCl. Okay. But this one is also going to be aqueous. All right. Let's do our chart here. So we've got iron. We have chlorine. We have sodium. And I'll show you how we can use the OH as one thing. All right. How many atoms of iron? 1. 1. Chlorine, 3. Sodium,
1.
and OH, 1. On the other side, how many atoms of iron?
1.
1. Chlorine,
1.
sodium,
1.
and OH, 3 of those. Okay. Well, where do we want to start?
Chlorine.
Okay. What should we do to balance it?
3.
Put 3 right here. Okay. So that changes our chlorine to a 3,
and sodium.
but it changes our sodium as well. Okay? Now what?
Sodium.
You want to fix the sodium? Okay, what are we going to do there?
We put 3 at sodium.
Right here? Okay. But it also changes our OH to 3 as well. Okay.
So that's the answer.
This is our answer. This is our balanced equation. Okay. Once again, like I said, we can always double check. 1 iron, 1 iron. 3 chlorine, 3 chlorine. 3 sodium, 3 sodium. 3 hydroxides, 3 hydroxides. As long as you can have everything the same on both sides, you're done. That's your balanced equation. It comes down to we have to account for all of our matter. Okay? We cannot be finishing with more or less than what we started with. Okay? It just that does not work. That does not work. So there is a table on 286 with some basic, like it lays out the different steps. It's basically what we talked about. There is one step on there that I didn't mention. If you were going back and forth with a couple different steps, it's possible that you could end up with something that looks like this. Okay. Now that is technically balanced. 2 iron, 6 chlorine, 6 chlorine, 6 sodium, 6 sodium, and 6 hydroxides, 6 hydroxides. That's technically balanced. It is good practice to write it in the lowest possible ratio, though. So we can divide all of those numbers by 2, and so that's what we do. Okay, we leave that as a 1, 3, 1, 3. So just be aware of that. If you can reduce your coefficients, you should. All right, and that actually is the end of this section. That's all I wanted to get to today. I do have a short homework assignment for you, but I'm going to give you the last 15 minutes to start on. And, you know, it won't be due for a week and a half anyway. So it is in chapter 9 now. And the numbers are as follows. All right, so you can go ahead and get started on that. Let me know if you have any questions.